Yes. Okay, cool. So today we're really happy to have Bing here from Department of Engineering to talk about the use of fiber optics for leakage detection.
Okay, thank you. Hello everyone, I'm Bing, and I'm a first year PhD student from the Department of Engineering, and my current research is about the traffic infrastructure. Before I came here, I did my undergraduate degree in the College of Civil Engineering in Churchill University, China. And this presentation is about, the first half is about my final year thesis, and the second half is when I came to Cambridge, I was surprised to find that some of my colleagues were doing the similar thing, so I got advice from them and was able to continue that as a side business. Okay, so its name is Fibre Optic Sensor for Thermal Pipeline Leakage Detection. But first, let's say something about civil engineering. Civil engineering first got its name as a contrast to military engineering. So everything, the buildings, bridges, roads, if it's not for the military purpose, then it belongs to the civil engineering field. And these pictures are some excellent examples. This is the Oriental Pearl Tower in Shanghai. It's a TV tower. And this is the Saint-Gina boat bridge in Switzerland, and it is voted as the most beautiful bridge in the world. And this is the Churchill. Maybe some of you may know. This is the largest underground project in the UK right now. Whatever you may think of these pictures, maybe nice pictures, or maybe beautiful architectures, or maybe the wonder of human wisdom, but in the eyes of civil engineers, they are the concentrated masses on each column, and the bridge is like two beams with a pin support in the middle and supporting at the both ends, and the tunnels are simplified as 4 segments with pins connected between them. And now it's the question time. My first question is that, do you know who he is?
Mao?
Yeah, very good. He is Chairman Mao, the founder of People's Republic of China. Now in China, nearly every university at the most salient place, you will find a huge statue of him. But none of them are the same. And they will tell us something about the university. And my second question is that, can you guess which is from a civil engineering school? The right. Why?
I guess there's a chance.
Yeah, that's a good guess. Because
What's stable?
It doesn't fall over.
this reaching arm is a huge cantilever beam. If you don't have enough mechanical engineering knowledge, it will fall down. You cannot design it properly. And actually, this is from my undergraduate uni. It's the biggest civil engineering university in China. And this one is from Fudan University, and it's our neighbor. It's also the top 3 university in China, but they are famous for social science, so they cannot do the design.
I think they are also good in math.
Good what?
In math.
In math.
Yeah, for that.
In math, also philosophy and other engineering, but not mechanical and civil engineering. Okay, about some trends in civil engineering nowadays. We are building higher and higher and digging deeper and deeper, and also trying to build structures in the earthquake area and also in extreme weather, of which I found really cool video. And also, we are doing health monitoring of existing structures, because in developed countries there are very limited land for us to build new structure, so we can only do the maintenance. Have you seen this before?
Oh, wow.
This was a newly constructed bridge, and a group of people was shooting films near the bridge, but they found this. It was vibrating so seriously in the big wind, and the people said, "No, let's stop shooting the film. Let's shooting this." So they took this.
Isn't that the Bahama Bridge? Is that right? Yeah, it is.
Oh my god.
That's pretty interesting. Maybe similar thing in Russia, in Bulgaria.
So the bridge collapsed due to this huge wind, and this is a very important event in the history of civil engineering. So before the collapse of this bridge, we don't do the structural design in wind. But nowadays, whenever we design very slender structures such as skyscrapers and the long span bridges, before it is constructed, we put the model, a scaled model into the wind tunnel, and we see if it can pass the test. If it cannot pass the test, then it cannot be built. Can I switch to my own laptop?
If it makes it easier to you, we can switch. But if it's the same, we can just leave it
I
online.
changed it later. I've changed it.
Okay.
Very interesting. The beams that look something like that. And that's what it's not the wind which was that, but the beam started rotating because of the wind. So that's why it started moving up and down. There was one car looking at the dog.
Okay, so that's about the design, the wind resistant design. And in my undergraduate uni, we have 3 wind tunnels, and I think they are the largest one in China. So that's why my uni was so famous. Is so famous for civil engineering because we have good devices, we have good tools. And apart from that, another trend in civil engineering is that we are doing more structural health monitoring because there is no opportunities to build new structures. And structural health monitoring, in other words, is called maintenance. And this is not very exciting like building new structures, but very unfortunately, this is what my undergraduate thesis is about. And what I'm maintaining is not buildings, not bridges, and not tunnels, even not roads. What I'm looking at is underground pipelines, so making it much more unfortunate.
I'm excited to see.
Clearly.
But why would I still choose it? Because although you may think they are ugly, but they are really important. They are called the lifeline system, and they are everywhere. In specific, I'm looking at the thermal pipelines, and they are used widely for district heating and also industrial purpose, such as transfer the crude oil. If you heat the crude oil, heat the temperature up for a little bit, then the viscosity will reduce and you will need less energy to transport it. So they are widely used. And because they are buried under the ground, so the leakage detection becomes a problem. Traditionally, we use visual inspection, that is to let the inspectors to walk along the pipeline, and if they spotted a pond of water, they will say, oh, there's a leakage beneath the ground. But at that time, the leakage is already very serious. And over the years, people have discovered a lot of new methods, such as using acoustic methods to listen to the noise caused by the leakage, and also to do the infrared scanning. But the acoustic methods and also the visual inspection, they are not efficient and very labor intensive. And the infrared method, I think they work better in the laboratory. And so what we are proposing is a completely new method, that is to use fiber optics. I think you all heard of fiber optics. They are widely used for the communication and also illumination, but they are also sensors. They can sense the strain and temperature. And I brought some fiber optics here for you to look at. the red ones, they are the temperature type fiber optic sensors, and the blue type are the string sensors, and also some black one are fiber optic cables. They have steel bars inside, so they can be stronger. And the one I'm holding is a connector. It's at the end of the fiber optics. It can link the fiber optics to the analyzing device. So how does it work as a sensor? Suppose this is a string of fiber optics. We connect it to a device at one end, and then the device is called analyzer. It can shoot light pulse inside, and most of the light pulse, most of the time, it travels forward. But at each location, a small fraction of them will reflect back, and this process is called backscatter. And the backscattered light, the property such as the intensity and frequency is related to the environmental parameter, such as the strain or temperature. And by analyzing this backscattered light, we can infer the temperature or strain in a particular location. And so how does this work as a leakage detector? We have underground pipelines, and when we're constructing them, we put a string of fiber optics below it. If it's a big diameter pipeline, we may need several strings around the pipe. So when leakage occurs, the hot liquid will leak out, and the ground temperature will rise up, and the fiber optics can detect this leakage. But fiber optics as a sensor has a big limitation, that is its spatial resolution. This concept is like the minimum division of a ruler. If you want to use a normal ruler to measure the micrometer level particle, you cannot get accurate result. And this is the same for fiber optics. If the temperature variation range is too localized, it's below the spatial resolution of the fiber optics, then you cannot get exact result. You cannot get accurate results. If we use fiber optics for leakage detection, this might also be a problem. For the commercially available fiber optic sensing system, nowadays the typical spatial resolution is 0.5 meters. And for the thermal pipeline, its leakage in the initial stage, the range of temperature variation is a question mark. We don't know. And with this question mark and 0.5 meters, which is larger, if 0.5 meters, the spatial resolution is larger than this temperature variation caused by leakage, then the fiber optics might not be a good choice to detect leakage. To answer this question, one of my senior students, she conducted an experiment. It's like that. She constructed a solar beam, which is 1 meter in length by 20 meters by 3 meters high. And this is the top view, and this is the front view. And she buried two types of sensors in the soil. One is the fiber optics, and the other is the temperature sensitive resistors. Or we might also call them TSR. And these TSRs, they are very accurate. Their temperature measurement accuracy, the error is below 0.1 degrees Celsius. So we can say they can give us the real temperature. And to simulate this pipeline leakage, she drips hot water to the center of the top surface, and after about 20 or 25 minutes, the temperature develops to a stable state. In the center, the temperature is higher, and at both ends, the temperature is lower. What she got from the experiment is like that. These blue points are the measurement results of the TSRs, and this red dashed line is the fiber optic measurements. And because we know the TSRs, they are very accurate, so this must mean the fiber optic measurements are not accurate. But the real temperature data points are too sparse, and we cannot easily visualize what's the difference. So in my computer simulation to get the real temperature distribution. This is my 1/4 model, and this is my calculation result. And it agrees well with the temperatures, with the TSR measurement, so I can say that my calculation result is relatively accurate. And now we can see clearly that the fiber optic measurements is wider and also lower. And also the temperature variation range is below the spatial resolution of the fiber optics. So we might say that, if we use fiber optics to detect leakage, we can detect this leakage. We can know that there is a temperature rise, there is something wrong with that, but we cannot get the exact peak value and also the range of the leakage accident. So at this stage, we are facing a choice. Should we continue with this idea, or should we abandon the idea of using fiber optics to detect leakage? And our answer is that we want to continue, and we also want it to work better. Very naturally, we would think that we will try to calculate this real temperature based on these not very realistic measurements. That's what engineers in real projects want. But for me at that stage, I'm thinking just the opposite. Because I know I have placed my fiber optics in a real temperature, but why it would give me a different result? I want to know how this flatter and lower result comes from. And very lucky this time, I'm not the only one thinking of that, and some previous researchers have been thinking the same. And this guy, Clark, he said something, published a paper trying to solve almost the same program, but from a very theoretical level. He said that the spatial resolution error is caused by the length and shape of the light pulse shoot into the fiber optics, and he thinks this error is caused by the light pulse. And based on some theoretical deduction, he said that each measurement of fiber optic is the weighted average of the real environmental parameter over the spatial resolution, and the wave function is a Gaussian curve. And these are all based on theoretical deduction. And he is researching on the string type fiber optic sensors, but we think it would work the same for the temperature type because their sensing mechanism are basically the same. So how do I translate this into my own experiment, into my own project? Suppose for this point of fiber optics, based on what he said, the measurement is the weighted average of the real temperature over the range of the spatial resolution. Because these are all theoretical deduction, I want to know if it would be the same for my project. Then I start to apply the Gaussian distribution weighing function to the real temperature and try to back calculate these fiber optic measurements. If all these are correct, then my back calculated results should agree well with these measurement results. And this is what I got. These colored solid lines are the back calculated fiber optic results, and they don't agree well with my experiment. So I'm thinking maybe the Gaussian weighing function doesn't work. Then how about other type of weighing functions, such as exponential distribution, or maybe log normal distribution? I tried several existing distribution functions and found none of them works really well. Then I began to think maybe the distribution function is not in a known form. Maybe it's something that we don't know, and I have to calculate it based on my data. Then I move to the second stage of my calculation. I keep the accept of the weighing average of the real temperature, but without assuming the weighing function to be the Gaussian curve. So it's like that for each fiber optic temperature measurement, the measurement is the weighted average of the real temperature over the range of the spatial resolution. We can discretize it into the summation form, and it becomes like that. And in my experiment, I have 16 fiber optic measurements. So I have 16 such equations and can get 16 W's. Maybe we can call them the elements in the weighing function. And how does this method work? It doesn't work well. And from what I got, these 16 numbers, the minimum one, the magnitude is minus 10 to the power of 8, and the biggest one is 10 to the power of 8. And between different points, there are huge fluctuations. And we can say that the result is almost nonsense. And why would it be like that? Because if we trying to think about the measurement mechanism of fiber optics, it's a very complicated process of electronic process, photonics process, and also influenced by the environment, by the temperature. So there might not exist a unique weighing function for all the measurement points. And by making them, by solving this linear equation system, I'm imposing a very strong constraint saying that you must have the same weighing function, but this is not the case. So I think maybe I step back for a step. I don't want the unique function that can make the right hand side equals the left hand side. I want an approximate solution that can maybe the right hand side is not exactly the same as the left hand side, but overall they would make more sense. They would be nearly the equal. So I move to the second step. The third step. That is trying to guess this weighing function. Of course, not guessed by human brain, but let the computer to do the work. I still have this real temperature and this element in the weighing function, but this one I like computer to give it a guess, and I can have this back calculated temperature. And the method I use is called genetic algorithm. If this back calculated temperature agrees well with my measurement, then I can say that my guess is good. If they do not agree well, then the guess is not good. Then I use genetic algorithm to do the whole thing. So I generate the initial generation of 50 weighing function, and trying to evaluate the fitness for each of them. So what does fitness mean? Fitness means the difference between my back calculated results and the measurement. And if they agree well, then the fitness score will be higher. Then after this first step, I keep the W with the highest fitness score, and for the rest, I mutate some of the elements and combining them into a new generation. I repeat this process until the highest fitness score has already reached my criteria. And this is my result. This is the real temperature, and this is the measurement, and this red line is my back calculated results based on genetic algorithm. Maybe it doesn't seem really good, but I think this has captured the peak value and also the range, so it works fine with the engineers. But as I said in the abstract, the genetic algorithm is not a perfect method, because when we think about our experimental process, it lasts about an hour. So and this is only the stable state temperature. So between the stable state and the initial state, how about the intermediate state? temperature rise up. Does this genetic algorithm works well? To test it, I applied the same weighing function I obtained from the genetic algorithm for the stable state to the intermediate states, and these are the results. Still the same. The blue ones are the real temperature, and the green points are the measurements, and these lines with huge fluctuations are my results, back calculated results from the genetic algorithm. And you may say that they doesn't look nice. Indeed, it doesn't look nice. But I think they still reflect some trend. For example, for this one, this is higher than this, and so I applied some curve smoothing technique, really simple one, and got this smooth result, like the pink line, and it captured the range and almost captured the peak value. So that is my result up till now. So these are my conclusions. For the thermal pipeline leakage in its initial stage, based on the experiment, we know that the temperature variation range is smaller than the typical spatial resolution of fiber optic system, and so the fiber optics cannot give realistic, very accurate temperature measurement of the leakage. And in order to get the realistic temperature from the fiber optics, we know that some existing, some known distribution functions such as Gaussian curves and exponential distributions, they don't work. And by solving linear equation system, it gives nice result. And the genetic algorithm is a potential method, although it might not work well for the other cases, but it's a good start point. At last, I would like to thank my supervisor in Churchill University and also several fellow students. We did the experiment together and also the simulation together. And also for my colleagues at Cambridge University, they gave me a lot of invaluable advice. Okay, and thank Courtney and Amanda for organizing this. Okay, thank you. Questions?
When you did this, when you used this genetic algorithm, did you use more temperature measurements? Or no? Did you use more temperature measurements than coefficients, or how? Because first you solved the whole set of equations, and now with the genetic algorithm.
Yeah, I can have more WIs. I can have more than 16.
Okay.
Yeah.
So when you used the genetic algorithm, you had more coefficients than temperature measurements, or
Yeah. I have
like
more than
measurement points, or what do you
Yeah.
call it, data points? Okay.
I have 16 equations, but I have more than 16 unknowns.
Okay, yeah,
Yeah.
makes sense. Yeah. So when you before you solved it directly,
Yeah.
and there you had how many? You had
16 equations
16 and 16
unknowns.
measurements. Okay.
Yeah.
What is the genetic algorithm originally used for? Like, why is it called a genetic algorithm?
Because it's like the biological process of evolution. Because you evaluate the fitness and the best fit individual can keep and pass to the next generation. For the next, they are not so good, so they have to experience mutation or crossover to be better fit to enter the next generation. Yeah. I don't know where it is initially used, but it got named because of the similarity.
I think often it's used when you optimize a system which has not one global minimum, so because there's some sort of random component, and then you can find other minima.
Yeah.
In the next slide. Okay, one more. Did you, so is that, do those functions use the original weighting, optimal weighting, which you
Yeah,
had
this is
before, or did you optimize GA for each of those?
I use the original weighting because I want to
Yeah.
search for
Okay.
uniform one. Tsubasa?
I was just curious that why the genetic algorithm fluctuates so much.
This one,
Yeah, like this one and the
this
next
one.
one. Yeah.
For this one, so you see each turning point is my unknown. So you can count how many turning points, then you will see how many unknowns I have here. So if I have enough unknowns, because for this case I don't remember, maybe 40, I don't quite remember. But if I have say maybe give me 1,000 unknowns, the genetic algorithm might take a very long time to run, but the curve is going to be very smooth. But for this one, the turning points, the location is the same as this one, but it has a larger fluctuation because for different cases they don't work as well as this stable state.
So is each TR term, TRX in your series, in your sums, is it
TSR,
if you go back 3 slides,
this
no
one.
more, 2 more, yeah, okay, this TRX, no that's too far away, 3 ahead, 1 more, and 1 more, the next slide, yeah, this one. So you have TRX xi times wi.
Yeah,
Is each TR just a polynomial, or
this one.
yes?
This one is the result I obtained from my
Okay, that's
simulation.
that's data point.
Yeah,
Okay,
the real temperature.
yeah, and then okay.
So the reason for the error in the fiber optic measurements, is that well understood? Is it a physical reason or is it the photonics?
It's a complicated reason. Photonics, electronics, environmental, and a lot of reasons. And what I'm trying to do is trying to find a explanation based on the phenomena. It's not the fundamental reason.
Because I was wondering if it, like for temperature, if it had to do with the fiber optic cable having high thermal conductivity or something, so the temperature just spreads out quickly over the cable. But if it's doing something similar for strain, then maybe it's more
Oh
complicated than that.
yeah, that might be one reason. But we have already used fiber optics to measure the temperature. So maybe I don't quite know.
Okay.
Yeah. Okay.
Makes sense.
Okay.
Yeah, could you explain how this method works? Anyway, I didn't get it really. Because you send light to the cable, then something happens to the signal, and how do you locate where something happened to the light while it was passing the cable?
You mean the fiber optics as a sensor?
Yeah,
This one?
yeah.
So it's a fiber optics here, and I connect it to the analyzer, and the analyzer can shoot light pulse inside. And light pulse, most of them go forward,
Yeah.
and a small fraction of them got scattered back because in the fibers there are some obstacles inside.
Yeah.
Yeah, and so at each point, some light pulse back scattered.
Right.
And by measuring the time, for
Mhm.
example, 1 nanosecond, I will know the location, and by analyzing the frequency, I will know the temperature. By
Mhm.
associating them, we will know the temperature at this location.
Oh, right. Good.
And it can sense the temperature through the sheath or whatever is on it.
Oh yeah,
Okay.
yeah. Because I have done some things very preliminary about how long does it take for the temperature outside to travel to the core, and what I found is that it's not a very long time. It's very quick. Yeah.
what are the next steps you want to undertake?
The next step, the first thing I will do is that I will apply it to more cases and see if I can find a unified weighing function. And if I succeed in that step, I will do the inverse process, that is to calculate the real temperature based on the fiber optic measurements. And that makes more sense for the real